Hello everybody, this is Mr. Kinney. This is part 4 of the acid review, acid equilibrium review. On the back of this paper here, this was our second packet. We've got all of these. Movie there. So, this is in the back here. I'm not going to go over every single thing on this. A lot of it we've done already in class. Why does a higher temperature cause a reaction to go faster? Well, the reason is you get higher temperature, increased temperature equals increased kinetic energy, which equals more particles flying around and colliding, and more collisions equals more reactions, more atoms slamming together, making a new bond. So more collisions equals more bond formation. Number 2, why does higher concentration make the reaction faster? Okay, if we've got 3 atoms in here, they're going to move around and they may or may not bump into each other. If we increase the concentration, so now let's say we've got 10 times the amount, those are moving around, they're more likely to bump into each other. Just like you and 3 of your friends in a closet, you could probably walk around and not hit each other. You get 30 of your friends in a closet, you're going to be bumping into each other. When you bump into each other, you make more collisions and you get more bonds. How does a catalyst cause a reaction to proceed further? Well, we're going to go to the bottom of the page here. So this graph is showing time going on. Here's reactants. This is reactants. Sorry, it didn't get written in there well. These are the products. And what happens is, for many reactions, say lighting the match, example I did in class, you've got everything you need for the match to burn, but it needs some energy to start it off. So normally we strike the match across the surface. It increases friction, gives us energy, and boom, then it starts the reaction. Once we get up here, the reaction starts going. We don't need to add any more heat because it's doing it itself. This is called, in fact, actually, question number 14 over here on this side. What is activation energy? I'm going to draw an arrow over here. Activation energy is the energy we need to bridge this gap. So adding heat, adding friction, something to get us over. That's activation energy, the energy needed to start the reaction. Now, to get back to question number 3, why does a catalyst cause a reaction to proceed faster? Catalysts will allow the reaction to go faster because it lowers the activation energy. So if we have a catalyst, let's say in the one with the match example, if we get the match heated up to like 350 degrees, it's not going to take as much striking energy to get it started. So a catalyst will lower the activation energy. Catalysts don't get used in the reaction. When you're done striking that match, that little piece of material is, the rough stuff, I don't have any here. It's still there. It's unchanged and ready to use in another reaction. Catalysts don't get used up in the reaction. Number 4. What happens to a catalyst in a reaction? I just said that. It lowers the activation energy. It does not get used up. It's ready to be used again. Catalyst works by lowering the activation energy barrier, shifting equilibrium, changing temperature, no particle. So what it does, it lowers the activation energy. That's how catalysts work. See, the rate of a chemical reaction, normally, what do we have? It decreases as temperature increases. Usually it's the opposite. You increase the temperature, they go faster. Let's see. Rates are slowed down by a catalyst. No, usually catalysts increase them. There's a special type of catalyst called an inhibitor that stops them, but that's not what we're talking here. Rates of reaction increase as reactant concentration increases. Yes, that's what we said there. That looks like a good one. Decreases. Now, so if you increase the concentration, you add more stuff into there, it's going to proceed quicker. Number 7, at equilibrium, what is the rate of production of the reactants? A plus B forms compound AB. And we're in equilibrium, so they go back and forth. So what is the rate of production of the reactants compared with the rate of production of the products? Well, these are our products. These are our reactants. At equilibrium, we're getting the rate of formation of the products equals the rate of formation of the reactants. At equilibrium, they're the same. That's why it's equilibrium. And it stays there unless we tweak it somehow. If a reaction is reversible, okay, like an equilibrium reaction, what are the relative amounts of reactant and product at the end of the reaction? Well, that's going to kind of vary, because in this reaction here, A plus B changes into AB. It could be, depending upon the reaction, and this is beyond the scope of our class, it could be that you're going to end up getting more of the product form and less of this. Now, when I do the arrow like this, I'm just saying we're getting more of this formed. So this means this is equilibrium, but this is favored. We're going to have this much of that, and we may only have little tiny bits of A and B. But at equilibrium, once they react, they're going to be changing into AB or back to A and B at the same rate. So let me make sure. If it's reversible, so again, it depends. Some reactions will favor products being formed. Other ones, it could be just the opposite. You might have a reaction where A plus B in equilibrium, it might tend to favor these guys being formed. So you have very little AB, but you have higher amounts of this. But at equilibrium, there's still just as much of this is being made as this. You just may have a bunch more of that. Okay, you got the problem here. Sulfur dioxide and oxygen can be made into sulfur trioxide. What is the reverse? Okay, we want sulfur dioxide and oxygen made into sulfur trioxide. So we just got to find, okay, it's a word problem. So we want to make sulfur trioxide. Well, okay, we're not making sulfur trioxide there. This is sulfur pentoxide. Make sure we want sulfur trioxide, so we're not making that. Oh, here's some sulfur trioxide. And there's no, okay, just by process of elimination, this is the only one that's making sulfur trioxide. We have sulfur dioxide and oxygen. Okay, there was the answer. That was just reading the problem and working it out. We've got this equilibrium reaction that we've worked with in class. What is the effect of decreasing the volume, which means increasing pressure? We're increasing pressure. So we got to take a look. Now, these are all gases. We have 1 mole of nitrogen, 3 moles of hydrogen. We have 4 moles of gases in the reactants, and we have only 2 moles of gases over here in the products. So what tends to happen is these 4 moles, see 22, every mole is 22.4 liters. So 4 times 22 is roughly 88 liters. Draw a big bubble, 88 liters of gases. Over here we only have 2 moles. So 2 times 22 is about 44 liters. So we don't have as much gas of the products over here. So if we start squeezing this, what's going to be affected first? If we're reducing the volume, increasing the pressure, this big reactants over here are going to be squeezed into these little ones because the products take up less space. So if we increase pressure on this one, equilibrium is going to shift to the right because we want to go from where there's more moles of gases towards where there's less mole of gases. Number 11, what happens to a reaction at equilibrium when more reactant is added to the system? Okay, well, if these are our reactants, if we add more reactants, equilibrium is going to shift that way, to the right. Wherever you add stuff, equilibrium shifts away. All you need to know. Number 12. Which of the changes listed below would shift the reaction to the right? So we want to shift the reaction this way. So let's see. If we add Cl, no. If we add Cl over here, if we're adding stuff, it always shifts it away from where we add. No. Let's see. Removal of oxygen. Okay, now if we take away oxygen here, if we take away something, equilibrium shifts towards where we take away. And we want it to go the other way. No. Okay, let's see. If we increase the pressure, decrease. Oh, okay, we got to look at the gases, the gas moles. 4 moles of HCl gas, 1 mole of oxygen gas. We have 5 moles of gases on this side of the equation. Over here we have 1, 2, 3, 4 moles of gases. So we have more moles of gas. This would be a bigger bubble of reactant gases than this one. And when you and we're saying we're increasing pressure, let's see. So if we increase the pressure, that's going to shift from more moles to the, hey, that's going to shift it to the right. That's what we got. Well, let's just see. If we decrease the pressure, well, if we increase, it goes from more moles to less. But if we are increasing the volume, we're decreasing the pressure, we get more space, it's going to go the other way. So anyway, this is the answer there, what we're looking for. Number 13. You know what? I'm not going to go over this right now because we have gone over this. Okay, I'll go over every other one right now just to save some time. Here's our reaction. Okay, PCl5 is added. PCl5, that is a reactant. We add a bunch of stuff on this side of the equation. It's going to push the reaction that way. Right now I'm just doing rates. If PCl5 is removed, okay, if you take away this, equilibrium shifts towards it. So towards the left. If we add heat, now in this problem I recommend when you see 30 kilocalories, write heat when you're taking the test so you don't think, oh, there was no heat in the problem. That's heat, energy. So if we add heat, that's increasing the reactants, it'll shift it to the right. If we take away heat, if we pull the heat out of here, put it in an ice bath, it's like we're removing a reactant, it's going to shift it to the left because it's want to make more heat. If we are adding PCl3, so that is over here in the reactants. If we add more of this, shifts it to the left. If we remove the same thing, okay, now the opposite. If we remove that, if we take that out, it's gone, it's going to try to make more. Oh, my lights just turned off here. Let's see. Usually they turn on, they rarely turn off. Cl2 is added. That is one of our products. If we add a product, it'll shift towards the reactants. It's going to shift us to the left. If we remove Cl2, oh, let me zoom out because you can't see here. If we take away a product, it's going to shift us more towards making more of the product, shift to the right. Because again, whatever you remove, equilibrium shifts there. If we apply pressure to this system, okay, we look at the gases. We have 1 mole of gas in the reactants. We have 2 moles of gases in the products. So if we apply pressure, we increase the pressure, it's going to go from more moles towards less. More pressure will make equilibrium shift that way. And let's see. I'm just going to talk about adding, and I'm going to talk about if we remove something here. So in this one here, we said in the very first, and then I'm done. You can figure it out yourselves. If we're adding PCl5, equilibrium goes to the right. So what's going to happen is we're going to be making more PCl3, the products. All the products will increase. The chlorine constant, we'll make more chlorine. In the process of doing this, we're going to lose some heat because it takes heat to make these. We've got a bunch of this added. We're going to use up this. So we're actually going to lose some heat. It's going to take heat to make that. The heat will decrease because it's going to be used up by this to make that. Now the opposite, if we're adding this right here, if we add a bunch of this, what's going to happen is it's going to shift equilibrium. Wait a minute, did I take that back? We remove PCl5. Sorry about that. We take this away, equilibrium is going to shift towards the left. And if we're going towards the left, we're going to be making a bunch more heat. So we're going to get heat will increase because we're making products now. Or, excuse me, we're making reactants. Zoom in so you can see that. Now, since we're also going this way, we're going to be, since we're making this stuff over here, we're going to be making this stuff using this. So the PCl3 concentration will go down, and the chlorine concentration will go down as well, because we're using up these to make that. I'm going to stop there. Thank you, and do awesome on the test.